So continuing on with trigonometric equations into section 7.5, we're going to discuss more different kinds of trig equations and some of the strategies that go into solving them. So starting out here, let's look at several examples, with the first one being 1 plus sine theta is equal to 2 cosine squared theta. So this is not really a situation where we can factor, but it's a situation where we can apply identities. So the identity that we'll focus in on here is 1 for cosine squared theta. That's equal to 1 minus sine squared theta. So if we put that here in our equation, we'll have 2 times 1 minus sine squared theta. And by doing this, we have rewritten the equation so that everything is in terms of the sine. I'll go ahead and distribute the 2 and rewrite this as 1 plus sine theta equals 2 minus 2 sine squared theta. Now in this kind of scenario, we will be able to now get it into a situation where we can factor, and we're going to factor by getting everything on one side. So I'm going to add this 2 sine squared theta over to the other side. I'll also subtract the 2 from both sides. So that I'll change this into 2 sine squared theta plus sine theta minus 1 is equal to 0. So let's see if this one will factor. We'll think of it as 2x squared plus x minus 1. And a trinomial like that will factor into 2x minus 1 and x plus 1. So our equation will factor to be 2 sine theta minus 1 times sine theta plus 1 equal to 0. Okay, if we set each factor equal to 0, we'll have two equations to solve. First one, sine theta equals 1 over 2. If we take the sine inverse here, solve for theta, theta will be sine inverse of 1 over 2. And so theta would be equal to pi over 6 and 5 pi over 6. If we add plus 2 pi n to each of those, we get all solutions. Over here, we have sine theta equals negative 1. And if we take sine inverse of both sides, we'll have theta is equal to sine inverse of negative 1. That gives us one angle for theta. Theta equals 3 pi over 2. With a plus 2 pi n, that would represent all solutions. So together, these are all solutions to this one. Now, one distinction we're going to make in this section are talking about solutions in the interval between 0 to 2 pi. And that basically means all the solutions within one rotation around the unit circle. So for this particular situation, we only have 3 solutions in one rotation: pi over 6, 5 pi over 6, and 3 pi over 2, since adding 2 pi to any of these or subtracting it will take it outside of one rotation between 0 and 2 pi. Now let's look at this one. 2 cosine x minus 5 equals 3 secant x. To solve this one, probably the first thing that would help out is to take the secant and write it as 1 over cosine. In this case, we can write it as 3 over cosine x. Now, in order to simplify this down to solve, I'm going to multiply both sides by cosine x. So that allows me to reduce this side down with the denominator. On the other side, I'm going to distribute the cosine x. So I have 2 cosine squared x minus 5 cosine x is equal to 3. We'll go ahead and subtract the 3 over. 2 cosine squared x minus 5 cosine x minus 3 equal to 0. And this is a situation where we can go about factoring this thing, thinking of it as 2x squared minus 5x minus 3. Let's see, this would be factored be 2x plus 1 and x minus 3. So our equation would go 2 cosine x plus 1 times cosine x minus 3 equal to 0. We set each factor equal to 0. We're going to have cosine x is equal to negative 1 over 2. And when we think about the inverse cosine here and the different solutions for x, we'd have 2 different locations where the cosine is equal to negative 1/2. That would be 2 pi over 3, and that would be 4 pi over 3. Now for this other one, if we try to solve for x, we'd get cosine x is equal to 3. And applying the inverse here, won't go too far because x equals cosine inverse of 3 does not exist. It's outside of the domain of the cosine inverse. So we have 2 solutions, these 2 right here. Now generally we again add plus 2 pi n to both of those. That's for all solutions. And then the solutions in the interval between 0 and 2 pi would only be the 2 pi over 3 and 4 pi over 3. Now we're going to look at this equation. Sine of 2 theta minus cosine theta is equal to 0. Now there's no factoring or anything like that going on at the start. And we do, though, have this sine of 2 theta, which is a little bit different. What we'll be able to do here is actually use the double angle formula for the sine of 2 theta. So if we go back to that formula, sine of 2 theta is 2 sine theta cosine theta. So it'll be a lot easier to try to solve if I take that sine of 2 theta and replace it with the double angle formula. So we're going to make this equation look like 2 sine theta cosine theta minus cosine theta is equal to 0. And now this sets up better because cosine theta is a common factor of both terms. So we can actually factor out the cosine theta. That would make it look like cosine theta times 2 sine theta minus 1 is equal to 0. We can now take each of these factors and set them equal to 0. Okay, in the first situation, if I want to solve this one, I can take the cosine inverse. Think about the angles where the cosine is equal to 0. So there are 2 locations where that happens, at pi over 2 and at 3 pi over 2. On this other equation, if I solve, I'd have sine theta equals 1/2. Considering the angles where that happens for the sine, there will be 2 locations, at pi over 6 and at 5 pi over 6. So if we add plus 2 pi n to each of those, that's going to give us all solutions. And then if we want to write down the solutions in one rotation between 0 and 2 pi, that'll just be the angles pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6. This one is cosine theta plus 1 equals sine theta. Now this one, we don't have any identities or formulas that apply to it, so we're going to have to take a different strategy. The strategy that'll help us out here is if we square both sides. So I'm going to square this side here and square the other side. Now if we square both sides in any equation we're trying to solve, we need to make sure we check our solutions, because squaring both sides can possibly introduce an extraneous solution into our results. So if I square both sides, we're going to be looking at cosine theta plus 1 squared equals sine squared theta. Now what we're going to do first is to expand this cosine theta plus 1 raised to the second power. In other words, multiply cosine theta plus 1 times cosine theta plus 1. So that's like foiling it, expanding it out, doing all that stuff. If you multiply everything together here, we're going to have a cosine squared theta plus 2 cosine theta plus 1, and that's equal to sine squared theta. Now the trick at this point is to try to write everything with just the cosines. So to do that, we're going to apply an identity. This time the sine squared theta, we can change that into 1 minus cosine squared theta. And then we'd have an equation written only with cosines alone. Okay, so it looks something like this. Now what we'll do is we'll add over the cosine squared theta. We'll subtract the 1 from both sides. So we're going to have 2 cosine squared theta plus 2 cosine theta is equal to 0. Okay, now this one is not too bad to factor. Since it has a GCF of 2 cosine theta, we'll factor that. Give us 2 cosine theta times cosine theta plus 1 is equal to 0. Now we can set each of these equal to 0. We get 2 cosine theta equal to 0, cosine theta plus 1 equal to 0. So now we have cosine theta equal to 0, cosine theta equals minus 1. So if I take the inverse here, solve for theta, theta is cosine inverse of 0. So there are 2 locations where this happens. It happens at pi over 2, and it happens at 3 pi over 2. Now on this other equation here, we take the inverse, both sides. Theta is cosine inverse of negative 1. So let's see, there's only one place where the cosine theta is equal to negative 1, and that's at pi. Now what we're going to do is we're going to check our solutions to see if everything works out correctly. We'll start with theta equals pi over 2. If we plug that into the original equation, it would go cosine pi over 2 plus 1, and we're checking to see if that's equal to sine of pi over 2. Well, cosine of pi over 2 is 0 plus 1, and sine of pi over 2 is 1. So that does check out as a solution. If we check theta equals 3 pi over 2, and we plug it in, we'd have cosine 3 pi over 2 plus 1, and we're checking to see if that's equal to sine of 3 pi over 2. Well, cosine is still going to be 0 through 3 pi over 2 plus 1. However, the sine of 3 pi over 2 is negative 1, so these do not equal each other, and this is not a solution. The last answer we had got was theta equals pi. If we plug that in, we'll have cosine of pi plus 1, and we're checking to see is that equal to sine of pi. Well, cosine of pi is negative 1 plus 1. Sine of pi is 0, so this does check out. We have two of these that are correct, and one of them that got introduced, which is not a solution. So all solutions would be written like theta equals pi over 2 plus 2 pi n, theta equals pi plus 2 pi n. And the solutions between the interval and within the interval from 0 to 2 pi would just be theta equals pi over 2 and pi.
In order to solve this equation, we have cotangent theta plus 1 equals cosecant theta. I'm going to change the cotan and cosecant into sines and cosines. So cotangent, that's cosine theta over sine theta, followed by the plus 1, equals cosecant theta, which is 1 over sine theta. Now, since we have converted this into sines and cosines, we have the denominators and the numerators. And in order to solve an equation, usually what we do is we multiply both sides by something so the fractions reduce down. And we get rid of the denominators and so forth. Here we can multiply both sides by sine theta, because sine theta divided by itself is just 1. So we can cross that out, keeping in mind that on one side here we're multiplying everything by sine theta across the entire side. But we get to cross out those other sine thetas. So what will be left here is cosine theta plus sine theta equals 1. Now what I'm going to do here is a little bit seemingly unconventional in a way, but we're kind of stumped at this point because we can't really go any further with, say, identities or formulas. But what we can do is try this. Subtract over the sine theta from both sides. Now why am I doing that? Well, first off, it makes it look like cosine theta equals 1 minus sine theta. And in this form, I'm going to take both sides and square it. One reason why we might want to square is so that the cosine turns into cosine squared, and then identities will start to pop up at that point. So we'll be able to write this as cosine squared theta equals. Since this is 1 minus sine theta all raised to the second power, that's the same thing as 1 minus sine theta times 1 minus sine theta. And what you'll have to do is expand that out by foiling it. So the result would be cosine squared theta equals 1 minus 2 sine theta plus sine squared theta. Since we have mostly sines, let's convert that cosine theta now using the identity. Cosine squared theta is the same as 1 minus sine squared theta equals 1 minus 2 sine theta plus sine squared theta. Okay, and then at this point what I'm going to do is add over the sine squared theta to both sides. Ultimately, the idea here now is to write it in a form that we can factor. So we want to get everything on one side and see if it'll factor. So adding that over, let's go ahead and also subtract over the 1 from both sides. That actually causes it to go away. What we'll be left with here is 0 equals negative 2 sine theta plus 2 sine squared theta. Why don't we go ahead and kind of reorganize that a little bit. Let's write that as 2 sine squared theta minus 2 sine theta equals 0. Just sort of rearranging everything there. Now we can factor here. We can factor because there's a greatest common factor with the two terms that are remaining. And that factor is 2 sine theta. So we'll write this as 2 sine theta times sine theta minus 1 equal to 0. And then what we can do is set each of these factors equal to 0. 2 sine theta equal to 0. Sine theta minus 1 equal to 0. And first one here we divide out 2. So that would be sine theta equals 0. Over here we can add over the 1. Sine theta is equal to 1. And if you like using the sine inverse here, you can take the sine inverse of both sides. Considering then that theta can be found by the sine inverse of 0. And similarly on the other side, we take sine inverse for 1. So theta can be determined by looking into the sine inverse of 1. For sine to be equal to 0, there are two places where that happens, either at 0 radians or degrees or pi radians. For sine of theta equal to 1, there's only one place where that happens, and that's at pi over 2. So we technically have 3 answers that we get out here, 3 solutions for theta. Here's one thing though that we have to be real careful about. One thing that we just did was we had to square both sides. Since we squared both sides, there's a possibility that one of these numbers is not actually a solution. So we'll have to check each of these to see if any of these turn out to actually be sort of an extraneous number that's not a solution. So to do that, we'll start with theta equal to 0. If we go back to the original equation, again, original equation was cotan theta plus 1 equals cosecant theta. And we try to substitute that in for theta, it would look like cotan 0 plus 1 equals cosecant 0. However, there's an issue with that. Cosecant of 0 is undefined. So what that tells me is that we can't actually use this in our answers. It's not actually a solution. If we go through and we also do the same thing for theta equals pi, cotan pi plus 1 equals cosecant pi, the same exact thing will occur. Cosecant is undefined for pi. So pi also is not a solution. Now if we go through and check theta equals pi over 2, cotan pi over 2 plus 1, we're checking to see is that equal to cosecant pi over 2. Well, in this case, cotan pi over 2 is equal to 0, 0 plus 1, and cosecant pi over 2 is also equal to 1. So this is 1 equals 1. It checks out. This pi over 2 is the only number that we have that actually checks out of the 3 that we received. So we have 1 solution between 0 and 2 pi. Theta equals pi over 2. And then all solutions would have the form of theta equals pi over 2 plus 2 pi n.